Let us talk about this problem. We are given two linked lists and these linked lists have some common nodes. Say this linked list H1 is this one and H2 is this one. So these three nodes are common. So the idea is this: there is one node where they intersect and then they have all nodes common. We need to find that intersection point. So what is the intersection point here? 5, 8, 7, 10. From 10 we have all the common nodes, 9, 10. So 10 is our intersection point. So we need to output 10. So we need to write a function that takes hats of two linked lists. So if you are programming Java, it will be a reference only. Here I use C++ style function, so it will be a pointer. So H1, H2 hats are given and we need to return 10. Please pause this video and try to think of a solution. Think of any solution. We'll talk about two solutions here. One is big O of m plus n and big O of m plus n extra space. And then we'll talk about a solution which is big O of m plus n and big O of 1 extra space. So method 1 is easy to guess and most of you must have guessed it. The idea is simple. We traverse the first list and put addresses or references of all the nodes in a hash table, right? So I'm using hash set here. If you're programming in C++, you will use unordered set. If you program in Java, then you will use hash set. So you will put all the nodes of first linked list in a hash set. Now you will traverse the second list and you will look for every node in this hash set, every node's address or reference in this hash set. As soon as you find a node which is already there in the hash set, you will say this is the intersection node. So let me just explain with this example. So I'll create an empty hash set first and then I'll put all these addresses. Address of 5, I'll traverse the first linked list and put all the addresses in this hash set. Right? They all will go in this hash set. Now I'll traverse through the second linked list. I'll search for address of 9. It's not there, right? So I would continue. I'll come here. I'll search for address of 10 and I'll find address of 10 in this hash set, right? This is already there. So I'll return 10 as an output. So if we assume that hash set, search and insert operations are big O of 1, then we are traversing the first linked list and putting everything into the hash set. So let's say the length of the first linked list is m, then it is going to take big O of m time the second step and big O of m auxiliary space. Now let's talk about step 3. Step 3, what it will do, it will traverse the second list. So it will take big O of n time. And it will do a lookup in this same hash set, so it will not require auxiliary space. So the time required here is big O of m plus n and space required as big O of m auxiliary space. So this is the solution number 1. Now please think of a solution that works in big O of m plus n time and requires constant extra space. Let us now talk about method 2 of this problem. Method 2 works in big O of m plus n time and requires constant auxiliary space. The idea is this: you traverse the first list and count how many nodes are there in it. So 1, 2, 3, 4, 5, 6. So you store this count in C1. C1 is 6. Now you traverse the second list and count how many nodes are there in this list. So you run a loop you run a loop something like this: for current equal to H2, while current is not equal to null, current equal to current arrow next, right? And here you will run current equal to H1. This is how you will count the nodes in both the lists. So C2 is going to be 4. Now you subtract the lower value from higher value, mainly you find the absolute difference. So the absolute difference here is 2, right? This is 4 and this is 6. After finding the absolute difference, you find which list is having higher nodes. That you can find out by comparing the counts, right? So here I figure out that H1 is having more nodes. So what I'll do is I'll traverse this h1 this many times, right? Say I get this value as d. D is absolute of c1 minus c2, which is 2. So I'll traverse this list 2 times, right? And after I traverse this list 2 times, I come at this node after moving 2 positions ahead, right? So from one, currently I'm here, after 1 movement I'll come here, after 2 movements I'll come here, right? Now what I'll do is, say this is my current 1 and I begin current 2 from here. Now I move both current 1 and current 2 simultaneously, right, from this node itself. And while moving, I simply check if they become same at certain point. They have the same node pointing to, right? If they're pointing to or referring to the same node. If they are referring to or pointing to the same node, that node is our intersection point. So I think you can find the mathematical reason also behind it. There are 2 things which have certain common part, right? So how do you figure out that common part? You cut down the extra part in this. Now they are of both same length. How did you cut down? You traverse this bigger list d times in advance, right? Now they are of both length and they have something common. So if you move ahead in both of them at the same speed and simultaneously, you will end up with the common part, right? And the first common part that you see is your first intersection node. So what we basically do, we run a loop which is like this: while current 1 is not equal to null and current 2 is not equal to null, and what we will see, we will say that if current 1 becomes current 2 at any point, then we return current arrow data, current 1 arrow data or current 2 arrow data, it's same, right? Otherwise, we simply move current 1 is equal to current 1 arrow next and current 2 equal to current 2 arrow next. And if you do not find any common nodes, if you never, went into this if condition, then what do? You return some value -1 to indicate that there is no intersection, right? So this is a solution that works in linear time, requires constant extra space.